Good morning. My name is Sharon Brody-Geva. I am from the University of Michigan, and I will be session chair for this very, very interesting session, which I think will be one of the more beautiful visually. The talks in this session will both show ways to provide knowledge from vast amounts of data to communities that are not the regular research community. In the first one, we will have Anders Ynnerman from the University of Linköping in Sweden. He's going to be talking about the OpenSpace initiative. Professor Ynnerman received a PhD in physics from Goddard University in Sweden. During the early 90s, he was at Oxford University, UK, and Vanderbilt University in the US. From 1997 to 2002, he directed the Swedish National Supercomputing Center. And then until 2006, he directed the Swedish National Infrastructure for Computing. Since 1999, he has held the chair in scientific visualization at Linköping University and is the director of the Norrköping Visualization Center. Dr. Ynnerman is a member of the Swedish Royal Academy of Engineering Sciences and the Royal Swedish Academy of Sciences. In 2007, Dr. Ynnerman was awarded the Axo Nobel Science Award, and in 2010, he received the Swedish Knowledge Award for dissemination of scientific knowledge to the public. In 2017, he was honored with the King's Medal for his contributions to science, and in 2018, he received the IEEE VGTC Technical Achievement Award. Please welcome Dr. Anders Ynnerman.
Thank you very much for that beautiful introduction and for being able to pronounce all the Swedish umlauts. That's not so easy. Thank you very much. It's great to be here. Great to be able to present to you one of the most exciting projects that I've ever been involved in, called OpenSpace. And I'm here representing both for myself, Anders Ynnerman. I also have Alexander Bock, who is unfortunately not able to attend this year. But I have Micah, who's sitting right here, who is going to help us with some of the demos during the talk. My story really begins already back in 1969. This is a picture of my grandmother's television set. Guess what I was doing in 1969? I was watching the landing on the moon. This really inspired me. It really inspired a whole generation of young people at that point in 1969 and had a tremendous impact. And the impact on me was pretty clear. This is me, Christmas Eve, 1969. They gave me a space helmet. You know, I refused to take it off for several weeks, and the only way that they could feed me was to open the visor and feed me sandwiches through the hole there. But you know, it was the starting of a whole career for me in physics, in mathematics, engineering, and eventually I ended up being the proud director of the National Supercomputer Center. And many of you recognize this fantastic old Silicon graphics machine, the Onyx 2 Infinite Reality Monster, and I was so proud of this machine. But that machine in itself really made it possible for me to return to my original mission and my passion for space, because I happened to bump into this guy, Carter Emmert from the American Museum of Natural History, back in SIGGRAPH 2001. And Carter had just produced one of the most amazing fly-throughs of the Orion Nebula for one of the productions for the Hayden Planetarium in New York. And many of you, I'm sure, have seen that. What we started doing was to think about the future. What can we do if we start looking at real-time interactive graphics? What can we do? And we had this vision to browse the universe interactively. This was a crazy idea because it really meant that we wanted to contextualize data from space missions, from observations, from simulations, and all in the context of one big digital universe. With scalable graphics ranging from dome theaters to laptops, everything. Also with interaction like VR, tablets, gesture, voice interaction, whatever you have it, but also to be able to support the explanation and the exploration of science, both in a science communication paradigm to children, and at the same time to the researchers themselves. And of course, it should be open source. It took us quite some time to do this because we realized that there were quite a few challenges involved in doing this. There's a challenge of spatial and temporal scales, visualizing things going from the millimeter scale up to billions of light years, going beyond the precision of the computer architectures we had at hand. The variety and the size of the data that we had to put into the system to be able to reach these goals, and also using experimental setups for collaborative and immersive visualization, and not to speak of the fact that everything that can break will break in a public setting when you have children playing around with your software. It took us almost 10 years before we reached a point when we could start up the OpenSpace project. And we really had to pull some of the best organizations together. There's, of course, AMNH up on the left-hand side, but also the experts at the Goddard Space Flight Center. The Ski Institute in Utah, at the University of Utah, one of the most famous institutes for computer graphics and visualization. Researchers at NYU, and of course my Linköping University, Norrköping Visualization Center at the top up there. But also a number of science institutions all over the world that we connected in this whole effort. And I'm happy to say also that we have the Gates Planetarium here in Denver as one of the partners in the OpenSpace project. But it's really about the people. Everything ranging from very senior scientists to the students that have been working on developing this piece of software. And I just wanted to single out two of the people who have been very instrumental today. Here's Micah sitting right here, and here's Alexander Bock, who is the lead programmer for the whole OpenSpace project. And if you happen to wonder who's the old man standing next to Alex here is, I can tell you that it's Charlie Duke. He's one of the Apollo 16 astronauts. So that's the picture that Alexander is most proud of. Now, OpenSpace has really been delivering many different contexts and many different events that we have been supporting. And some of them have been quite spectacular. Look at the one down here on the left, where we are actually following in 2015 the New Horizons mission when it was flying by Pluto. And we were doing that live. So we had 11 planetariums worldwide that were connected using OpenSpace. We had Neil deGrasse Tyson sitting in New York, myself in the city of Norrköping, and we were simultaneously visualizing what was happening as we were flying by Pluto at that point. We were looking at the Rosetta mission, looking at the 67P comet flying by a few years ago, and the Philly lander that landed, or almost landed, on the comet. We even recreated history, putting ourselves on the back of Apollo 8, flying around the moon for the first time, and the famous Earthrise picture that we regenerated using real scientific data from the Lunar Reconnaissance Orbiter. But what I did for today was to pick 3 different cases that I felt could be of interest to this community here. So let me talk you through these 3, and then we will show you a demonstration of these 3 cases as well. The first one I picked is space weather simulation. And of course we have the Goddard Space Flight Center with us, helping us out with the work here. And if we look at the problem that they have in space weather, it's really about putting together a very large number of different codes and different models that are linked together to be able to predict space weather. And of course, what we are doing here is that we are helping out with the visual interfaces and the representations for science, but also for public dissemination about space weather. Now, the typical setup that they have is the analysis tools at the modeling center. They have their own in-house computer systems with reasonable resources, generating lots and lots of data that needs to be analyzed. And coronal mass ejections, like you're seeing here over the solar systems, can be very problematic. Now, what we wanted to do was to take all of that data that's inherently spatiotemporal in 3D and volumetric, and make some really beautiful visualizations that could be used for dissemination and for science. But to be able to do that, we had to figure out nice ways of representing the terabytes of data that's coming out of the simulations. So we designed our own little space-time partitioning system where we have a binary search tree with octrees on each of the nodes. That means that we can split either according to time or according to space at any given time, so that we can have a feed of the data that we are storing in a very intelligent structure. So at any given time, when I'm playing back data, I can choose whether I need higher resolution in space or in time. And if I do that, it looks like this. So this is the whole solar system. Now you're inside of the whole digital universe, and you're looking at volumetric data that's rendered in real time inside of OpenSpace. You have the solar system, and you have the stars in the background in their accurate locations. This is actually data coming from the New Horizons flyby of Pluto. So we are actually simulating, looking at the space weather conditions during the flyby, 2 weeks before and 2 weeks after. And if you want to look at this in a dome theater, you just migrate over to the dome and you can make a wonderful presentation about science to a large audience. The second example that I wanted to bring up is planetary science. And really what we want to do inside of our own whole digital universe, of course we need planets and planetary surfaces with time-varying data, with high-resolution data over the planetary surfaces. So we developed our own system for this, and we call it globe browsing. It really starts off with the tessellation of the planets. Then we add a map projection, and we have a wonderful open source library called GDAL that we can interface with to retrieve very high resolution images and slices of data across the whole globe, not only on the Earth, but also on other places. And then we put that together into a tree representation that makes it possible for interactive browsing of planetary surfaces. Now, there's a number of different sources, and it's amazing the amount of data that's out there, the data that is generally available to anyone. So we can put these layers in groups. We have color layers, height layers, water layers, night layers, different kinds of data that we can represent on the planetary surfaces. And most importantly, we can blend all of these together with a number of different operations. So this is typically what you would look at if you look at a planetary surface in the representation that you find. But what we wanted to do was to go a little bit further down into the details of this data. So let's take one of the regions on the surface of Mars and look at it like this. Now, what would happen if you used the high-resolution data, if you did photogrammetry using stereoscopic projection of these images onto the surface and extracted 3D models? What can we actually do? Well, then it looks like this. It's particularly that region that you were looking at. It's almost photorealistic with a very beautiful rendering of the atmosphere, but that's a separate talk in itself. And you can get these beautiful views. And the scientists themselves are saying, oh, we haven't seen it this way before. This is a brand new way of looking at it. And we get new insights that you didn't get from the global overviews that you had before. And this is all rendered in real time inside of OpenSpace. Now, the third example that I wanted to bring up is an example of very large data from observational astronomy. One of the most exciting data sets that we have to look at this moment in time comes from the Gaia instrument. The data release 2 that came out in 2018 with 1.7 billion stars. And quite a few of them have the parallax and the proper motion inside of it. And you will get to see this in a little while as well. Now, it's 1.2 terabytes that we have. And of course, what we wanted to do then was to represent that data in an intelligent way. So we had to build yet another tree structure and sample the data into this structure to make it possible to interactively browse through the 1.2 terabytes of star data from the galaxy. We also had to do some intelligent things with the rendering, because just rendering so many points is not possible on the GPU today. So we started doing screen space algorithms instead. So we're rendering pixels rather than 3D primitives. And that means that we can filter out for perception, and we can do some in smart way. And then actually, to get it onto a dome surface, we have to do a reprojection, an image reprojection onto the warp geometry, which was a little bit tricky for us to do. But it was worth it. Because what you have is 1 billion stars on the dome, interactively. And this is an image taken at the Gaia Sprint event at AMNH. And for the first time, the researchers and the astronomers could visualize on a huge screen all of their data interactively and fly through. And you can even see the Gaia instrument and the path of the instrument in itself up there. Those were the 3 cases. So if the demo gods are with us, we'll move into demo mode. And I would ask if we can dim the lights as much as possible in here, and we will turn over to Micah's computer. All right, here we go. Thank you. And we provide you with a little bit of space background music here as well. So Micah is now driving OpenSpace live for you on his Alienware laptop. And can we drop the camera view of me as well, please? Thank you. All right. So we're starting off looking at the space weather situation that we have. So let's start looking at the solar system. And we'll be zooming in. You have the whole solar system. You have Mercury, you have Venus, you have Earth, you have Mars, Jupiter, Saturn, Uranus, Neptune. And everything is localized inside of the whole universe. So we're free to fly wherever we want to fly. But we decided to start looking at the space weather simulation data. So every now and then there's solar storms. And we picked a particular data set. This is from the 14th of July in the year 2000. And Micah is going to just kick the data in for us, and we can see. Okay. 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 We have a time issue. There. Okay. So what you're seeing is the 14th of July coronal mass ejection and in the volumetric data. And hopefully we can get the time going here as well. Here we go. So you see the field lines from the simulation codes, and there goes the coronal mass ejection. One of the big class X events, and this is now happening all in real time rendered as you're seeing it. And of course this is one of those things that could potentially harm the Earth if it hit us. Just 10 years before this, there was an incident that hit us and knocked out most of the power grid in Canada. Now, we will be moving out, and we can leave the coronal mass ejection behind us, and we will be flying to Mars. Can you set the controls for Mars? And of course, the reason why we're flying here between the places is that just to show you that everything is happening in one view of the universe. So this is the browser that I talked about. So we're coming into Mars. You can see the 2 moons. You see Phobos and Deimos coming into view. And Mars, the red planet, it's a little bit reddish because it's iron oxide. It's rusty. And the representation layer that you're looking at now of Mars comes from the Viking missions from the 1970s. But since then, we've had missions orbiting around Mars. We have one called the MRO, the Mars Reconnaissance Orbiter. And one instrument on the the MRO. It's called the CTX camera. And I'll be asking Micah to press the button to kick in the CTX data for us. And I think we're rotating around to find some interesting places. Here comes the data. Usually we don't have the data residing locally, so it's distributed across servers all over the world. So we have an abstraction layer for the network, so you can basically tap into any resource out there and it will be kicking in. And you see it's not complete, there's data missing. And that's one of the things that we are trying to do in OpenSpace, is to not fill in the gaps. We're just showing the data. It's a pure data visualization that you're seeing. Micah is slowly flying in towards one of the interesting parts of the Martian surface. This is the Valles Marineris. It's like the huge canyon. It's like the Grand Canyon on Mars that we're going across over now. As we're moving closer, we're kicking in more and more resolution. And you will be seeing the dramatic formations, thousands of meters of drops down in the ravine. And we're very proud to be able to show you one of the examples of extreme resolution of the Martian surface, where we're flying in towards one particular part of the Valles Marineris called Chondrocosma. If you get a ticket to Mars, I can recommend visiting the Chondrocosma. It's a very beautiful place, and we're flying in here. Now, on the MRO, there is another instrument called the high-rise camera, and the high-rise camera is generating data with 25 centimeter resolution. And we're heading down towards one of the patches of 25 centimeter resolution now. So what you're seeing now is resolution that is essentially better than what we have in most places on Earth. And we're putting it in the context, and if we zoom in, you can see the very dramatic formations. There's a very strong wind blowing in the very thin atmosphere on Mars, creating these patterns, the wind patterns like you would find on a beach after a windy day. The sand dunes that you see now are approximately 25 to 50 meters tall. So we're down to the human scale. If we had cars, if there were buildings on Mars, you would start to see them now. And when we actually move down all the way down to the bottom resolution level, I'm telling you, if Matt Damon was here, we would see him now. Some of you have seen the movie, all right. Okay. But one of the great things about showing live demonstrations is also the fact that what you're seeing now is a unique view. Even though the data is here, it's on Earth, no one has ever seen before you what you are seeing now, because we're generating this in real time. And imagine the power of letting children, anyone out there, explore this and say, hey, you can fly to Mars, you can use OpenSpace, you can go there yourself. And you become the explorer of the unknown. Let's take off from the Martian surface. We really wanted to play some David Bowie here as well, but it would be a little bit cheesy this morning. So, okay. So as we're moving off from the Martian surface, I want you to keep one thing in mind when we're looking at space, and of course that's the speed of light. You have 8 minutes to travel from Earth, from Sun to Earth, and another 8 minutes to go to Mars. And what we will be doing now is traveling very, very far out into the universe. So we'll be pulling out, you will see the whole solar system in view, and we'll be pulling outside of the solar system. Then we will be approximately 12 light hours away from Earth. A little bit further out, we will be turning on representations of the stars as well. So here's the sun, the solar system, and you can see each individual star is now located in the accurate location. This is the Hipparcos data set that you're looking at now. It's pretty sparse. It's a few 100,000 stars in this data set. What happened after the Gaia mission? The 1.7 billion stars. Should we turn them on, Alec? There you go. Isn't it amazing the amount of data that we can get? In the Milky Way, we have about 300 billion stars. There's about 1 billion of them that are close to us. What we also have is sort of the radial velocity of these stars. So I'm going to ask Micah to play back this data 50,000 years per second, and we'll see what happens to the nearby stars around us. There you go. And the astronomers are going, hey, look at that. There's this cluster of stars that's not moving in that direction. So they see things, they see patterns inside of this data, things that they had not known before. Do you want to keep pulling out? I promised in the abstract the grand perspective on the universe, so I think we will give you that. So let's pull out. We can keep the Gaia data set on as we're pulling out. As I mentioned, there are about 300 billion stars in the Milky Way. It's 110,000 light years across from one side to the other. And now we're contextualizing the Gaia data set inside of the whole representation of the Milky Way. And we're turning on another subset of the Gaia data set, the upper part here. And now you're beginning to see the Milky Way in the background as well. Now it gives you the structure, the feeling, the notion of the plane of the Milky Way. And we have a volumetric representation of the Milky Way here as well. Now, as we're pulling out outside of the Milky Way, you're beginning to see other points in the background. Now, every single star in the background is another galaxy. This is the Tully data sets of galaxies stretching out to about 900 million light years out. You're beginning to see the structure of the universe. The galaxies are not randomly distributed, but they are like branches on a big galactic tree. And it's all data. There's no animations. Everything is data-driven. At a distance of about 1 billion light years away, we turn on other data sets. Here's the Sloan Digital Sky Survey that we're turning on, and the 2-degree field survey from the instruments in Australia. And now you can see one of the fascinating things about the data set. It's the fact that we are only looking at the directions where we have data. This cone-like structure of the universe is of course only an artifact of the sampling of the universe that we have done. It turns out it's hard to observe galaxies in the plane of the Milky Way. So the dark region is actually the shadow of the Milky Way itself. At this distance, you can stop a little bit here and just rotate around and let us look at this and reflect over what it is that we're seeing. What you're actually seeing now is a representation of the universe that has been sampled from the viewpoint of the Earth. So it means that the light information from these galaxies out here, 6 to 7 billion light years away, has been propagating towards us for 6 to 7 billion years. So in some sense, the further away we travel from Earth, the universe we're looking at is younger and younger and younger. So these are the galaxies the way they looked like 6 to 7 billion years ago. The data set is stretching out to this distance, and eventually we reach a distance when the universe is so young that there are yet no galaxies. But there's one other thing to look at out here. Those are called quasars. Quasars are objects that were discovered in the 1950s for the first time and puzzled the astronomers. What are these very bright sources of light that are so far away and redshifted, moving away from us? What is it? Turns out that it's probably gigantic black holes in the very early universe, consuming matter, generating energy in the gravitational collapse of matter into them. According to some theories, most of the energy that we have in the universe today originates from the collapse of matter into the early gigantic black holes in the early universe. A little bit further out, even the quasars disappear. And there's only one thing that's remaining to look at in the universe: the echo of the Big Bang itself, the cosmic background radiation. Current estimates, 13.8 billion light years out, 13.8 billion years back in time when the universe was created in the Big Bang. A few 100,000 years after that, the recombination when electron met protons for the first time, generating the cosmic background radiation that we now can detect from Earth. So this is sort of the end of the observable universe. Do you want to fly us back? So keep in mind 13.8 billion light years, and we're going to find a singular little planet on the way back home. Through the Sloan dataset, into the Tully galaxies, finding the Milky Way, and heading back home. Since this is an improvised demonstration, I would suggest we fly to the moon. I think we have time for that. Can we do that? Micah says yes. Thank you. Of course, the reason why I asked if we could fly to the moon is that 50 years ago, of course, we had the first landing on the moon. And we've had the privilege in OpenSpace to recreate many of those sites where we have had Apollo landings. So we will pick one of them. Why don't we pick 17, if you can do that? Yeah. So here comes the solar system. We're navigating back home. The inner planets are coming into view. You have the sun in the middle, and we will find the third planet, the Earth. The reason why we picked Apollo 17 is that it's, I refrain from saying the last, but the latest visit to the moon in 1972. And actually the only mission where we had a scientist. We had Harrison Schmitt, a geologist who was one of the astronauts on Apollo 17. Just as we had on Mars, we had extreme resolution data over the moon. We have the Lunar Reconnaissance Orbiter, and we have picked in the data. And in our globe browsing system, we can now identify some of the landing sites, and Micah is desperately trying to find the landing site for Apollo 17 here. I think he's finding the right spot right over there to the left. Great. That's fine. Okay. And of course, one of the reasons why we're doing this in OpenSpace is that many of these stories from 50 years ago are almost being lost for the next generation of young people. When I show this to high school children that are coming to visit us, they go, oh, is this real? Have people really been on the moon? And now we're flying down in the actual terrain of Apollo 17 with real data. It's not an animation. This is data from the LRO. And just like we have recreated the terrain over Mars, we have the terrain where Apollo 17 landed as well. We can even go down to the point where we can see the footprints and the tracks from the rover. On Apollo 17, they drove about 35 kilometers over the days that they were down in this valley down here. Here's Micah zooming in on the valley here now. Can you find the landing site too? All right. There we go. So you see this little spot right in the middle there? That's the landing site of Apollo 17, and those are the dark lines that are going out. Those are the tracks from the astronauts and the rover. And the little white shadow down there is actually the rover where it's still parked as well. So I could talk about Apollo 17 for about 2 hours, but I'm not going to do that here. So I think we'll leave you with a demonstration of the Apollo 17. If anyone is interested in talking more about this, I'm sure Micah is going to be around afterwards and can show you more about the Apollo landing site. Oh yeah, bring it up so we can see the terrain around here. Very nice. And you can compare the pictures that were taken on site. And being Swedish myself, I'm very, very proud of one thing. It's the fact that they had a Hasselblad camera from Sweden. So many of the pictures that were taken on the moon were enabled by Swedish technology. Okay. So we can switch back to my laptop. Please. Thank you very much, Micah. So what is it that makes all of this possible? Well, of course, it's the OpenSpace architecture, and I'm sure that some of you in here today can appreciate the details of this immense work that has gone into building the OpenSpace architecture. An architecture that is supposed to support everything ranging from live presentations in dome theaters, immersive screens. You know, I would have loved to show you OpenSpace on the full screen here today, but we didn't have time to set that up. It would have been really, really nice. But it's also a kit for anyone to develop content, because it's very lightweight in terms of how you provide modules inside of OpenSpace. It's also possible to go down to the lowest levels because it is open source, and you can configure, you can contribute with rendering algorithms at the lowest level if you want to. So we're addressing many, many different audiences at the same time. Because we have this nice architecture with a core of a set functionalities, we have the modular structure on top of that, where you can contribute with content. Every single scene that you have seen in the demo is essentially one module that is connected to the core functionality, that we are keeping a tight grip on that core. But then opening it up to anyone to develop user interfaces through scripting, third-party integration. And one of the most important things that enables us to move from laptops to supercomputers to big planetariums is the fact that we have a very nice toolkit in the bottom called the Simple Graphics Cluster Toolkit that we have developed over the years. You can configure anything, any viewport, with just a few scripting lines, and it will provide you with visuals that will span across fisheye systems, wide range system, multiple projection systems, etc., etc. So to the point when we can actually support things like laptops, you can download OpenSpace tonight. If you like what you see here, you can download it. And if you have a reasonable GPU in your laptop, you can run it on your laptop. And then it will scale up to touch systems, to planetariums, to clustered systems, everywhere. And you can even use it in production of fisheye rendered images that you can extract out. In setups, you can have systems like, for instance, you have a clustered system where you have really frame-locked projectors that are generating very nice views. In our system, we have 6 projectors in our dome with a master node that's running the whole things. Through our wormhole server, you can connect other sites, so you can share experiences. Everything ranging from laptops anywhere in the world to big planetariums can share the same content and the same presentations as well. In the DNA of the whole open source project is Lua scripting. And Lua scripting has really been one of the keys for us to enable all of the additions to OpenSpace. Everything is configurable with scripting. Configuration of the system in itself, every single interaction can be done through Lua scripting as well. So that's a very important ingredient in the whole setup. It means also that you can chain everything using Lua. You can have Java scripting going. You can design your own interfaces in Java if you want to. And even if you have a comprehensive system where you want to run a full show, you can have a very nice user interface with predefined features that you want to show in OpenSpace. now. Of course, what I would have liked to do is to bring all of you and put you in a dome theater and show you what OpenSpace can do, because it is a massive, unique experience to be able to fly through the universe in a collaborative session where you decide as an audience where you want to go. So anyone who can pronounce Linköping and Norrköping, you're all welcome to come to Sweden on your next vacation. And I'll show you all of this in the dome in a personal VIP show. So if you like what you see, you can download it. If you like it even more, you can work with us because we're hiring. So please approach us afterwards if you want to talk more about OpenSpace. And thank you so much for listening to me, and thank you, Micah, for doing the demo. Thank you very much.
Thank you again for this astoundingly beautiful voyage. And we have time for a few questions. If there's anyone who has questions. Oh, the lights are back up, so that will be easier.
Yes, absolutely. That's a question number two.
Number two?
So I suppose the SpaceX people and those that are looking for space exploration to charge people, now we can just put a Varo headset on and go there. So we're kind of sidestepping their space exploration. A different question back here on Earth. So the SCC is auctioning off 24 gigahertz, and the NOAA and meteorological societies are concerned about impact to weather forecasting in the United States. Is this a potential solution to work around impact of wireless communication, 24 gigahertz in local forecasting?
Well, you know, it's, that impact is what we can do with the OpenSpace project is to help in the analysis of the forecasting. And of course, the forecasting is then geared towards helping and assisting in shutting down systems in time, moving things in time, so that we get the notice. Whether we can, with our software, help in actually alleviating the problems in the actual communication of the frequencies, I doubt that. But we can certainly help in the prediction of what's going to happen and when it's going to happen.
I was wondering, how often are the data sets updated? So is it once the data's acquired, is it updated onto that?
Well, it varies a lot between different data sets. We didn't show that, but if we zoom in on Earth, we have daily images, so it's updated once a day. We have global weather. So as soon as any service out there provides an update of data, we get it automatically in OpenSpace because it's all depending on those providers of data. Other kinds of data sets where we have to engage and work with them, like for instance in the Gaia data sets where we need to develop unique data structures, it takes a little while. But the whole project is all about shortening the distance between science and the general audience. So, you know, the Gaia DR2 release in 2018 was in April, and we did that event that I showed a picture of in June. So it's really short time between data availability and dissemination.
Does that mean you would have the all the exoplanet data so that you could go to the...
We have that, yeah. So come up to Micah, we'll show you 4,500 exoplanets as well. Yeah.
On one?
Yes, so you showed at the end, towards the end of the simulation, the quasars, which you said are probably black holes. Do you have any data sets specifically relating to black holes?
No, we don't have any black hole data at this point in the data set, but it's something that as soon as something becomes available, we would put it in. But at this point, we haven't found any data source that will give us that capability that we need to be able to put it in. Yeah. Yeah.
How hard is it for you to onboard new data? Is it a zoo of different file formats or different data formats you need to deal with? Or is it like you click a button and you can onboard it? If I fly my drone, you can just use my data as well? Or is it...
There are specific formats that we are adhering to. And if you use one of those formats, we can certainly get it in immediately. We're trying to be very clear on what kind of data formats we are supporting. And of course, there has to be a few of them. But people like Micah has to develop new readers for that data if you have a particular kind of data. It's not as easy as flying your drone and putting it in tomorrow, but maybe, yeah.
So if there are no more questions, let's thank our speaker again.
Okay. Thank you.